Thank you for introduction.
Thank you, sir.
Let me, so my name is Tasaki. Professor Sako gave an interesting presentation that laid a foundation for my presentation because he talked about subcritical water, and I'm going to be using the same technology. Now, I'm with a company called Tomorrow Water, and we do a lot of things with water. And today I'd like to share with you a project that was born out of a new initiative called upcycling that we started a few years ago at the company. And the title is Chemical-Free Extraction of Value-Added Product from Organic Waste. And organic waste that we're talking about animal waste. More specifically, what's called keratinous animal body parts, or COWT for short. And these are things like hog hair, wool, feathers, beaks, hooves, nails, you name it. And as demand for meat globally grows, we're going to have a lots of these animal waste, and especially keratinous animal body parts are very difficult to treat, and mostly they are disposed at the landfill. So we're going to have to start thinking about what to do with this. How do I go to the next slide? Okay. So this is a supply chain of livestock production, and farmer would sell their animal to slaughterhouse where they cut meat to sell, leaving lots of animal waste behind that nobody wants. So they send animal waste to rendering plants where they do everything they can to recycle what's left of animal waste and send back to livestock farmers as feeds. But again, peas are very difficult to treat or recycle, so they send to landfill, which raises environmental concern. So the idea here is to recover something valuable from cow peas so we can close the loop for circular economy. Now, there are three commercial applications for keratin that people are looking into, some of which are available in the market. The one is cosmeceuticals such as hair care or skincare product, and feed additives or pet dietary supplements, which are growing. Thirdly, biomedical applications, most notably wound dressing or tissue engineering, which is a very active area of research. As much as I'd like to cover all of three areas, today I only have time for cosmeceuticals. Now, some keratin-based cosmeceuticals are already available in the market, which is growing rapidly, as you can see. And keratin happens to have a very interesting characteristics, such as anti-aging, rejuvenating, healing effect, which are really good to help you look young. Okay? And the desire to look young seems to be growing given increasing aging population. This slide is a little bit busy, but to give you an idea how complex the hair structure is. The hair is made of layers and layers of fibril, and there's another fibril inside the fibril. You keep peeling the fibril, you come to a basic structure showing at lower right corner called coil, where two alpha keratin helices are bonded together through disulfide bond or SS bond, which are very strong, along with the hydrogen bond and hydrophobic interaction between keratin proteins. They provide very strong mechanical strength to your hair. So the good news is every time you take a shower, your hair won't fall off. But bad news is that if you try to extract the keratin, keratin is very recalcitrant, given this structure. You can, however, extract the keratin if you don't mind using tons and tons of highly concentrated toxic chemicals such as these, which is called Shindi method, probably one of the best chemical processes out there. By using these chemicals, extremely environmentally risky, also raises production cost. In addition, processes are very time consuming, as you can see here. So instead, we decided to use an alternative process called thermal hydrolysis process, THP. Professor Sato was talking, we can call it subcritical process, the number of ways of saying that, but we're talking the same thing. And we're not going to use any chemicals at all, only water. And we do have our own proprietary THP reactor called COWT, as you can see here, for cyclic organic waste treatment. So why water? Water has a very unique characteristics at high temperature. So we're going to take advantage of that. Let me give you some example. Here's the solubilities of some polyaromatic hydrocarbons that we know do not dissolve in water at room temperature. But as you increase the temperature, their solubilities can go up as much as 3 to 4 orders of magnitude. The y-axis is logarithm. And they do dissolve in water at the high temperature. So why is that? That's because as temperature goes up, water becomes less polar. And favoring hydrophobic interaction, which is why polyaromatic hydrocarbon can dissolve. But this situation creates a condition that might help swell the tight fibril network I was talking about. And in my nature, keratin protein, now that hydrogen bonds are weakened. In fact, if you look at the direct constant of water, it drops as much as half, going from 20 degrees to 200 degrees. No wonder water becomes less polar. The other thing you notice from the table is that the dissociation constant goes up by 2 orders of magnitude, from 20 to 200 degrees Celsius, which means that water is acidic. In fact, pH drops as low as 5.5 as temperature goes up, which means you have more hydronium ion in the solution acting as oxidizing agent. Now that fibril structure is swollen, creating channels and pores, they may find their way to disulfide bond by breaking up and releasing individual keratin protein from the rest of the network. So this is the process of keratin extraction by THP. Perhaps watching speaks more volume than listening to a boring lecture like this. So I prepared a video for demonstration. We used chicken as an example, because chicken has full of keratin, such as feathers, feet, and nails. And it so happened that a few years ago, we had another pandemic that was avian flu, when lots of chicken died. So one of our slaughterhouse clients brought in a bunch of dead chicken, and we had to dispose them using our COWT reactor. So here it is. So he's trying to put in the dead chicken into a COWT reactor. He's kind of struggling in it because we don't do this very often, hopefully not in the future. But once you put chicken into the reactor, we can start reacting at 180 degrees Celsius for 30 minutes. What you're seeing here is a full-scale COWT reactor. At the end of the reaction, from the bottom of the reactor, here comes out the liquid. So you start with a whole chicken and end up with that solution. So you get the idea how powerful a COWT reactor is. So here's a bench scale COWT reactor that we used for our experiment. It's smaller than what you saw in the video, but it does what it's supposed to do. And there's a 2-liter capacity reactor vessel sitting inside the box. And then we used the Hog Hair as a sample, but you can use any other cow peas, such as wool and feather. And then we ran a series of THP experiments at different temperatures. I'm only showing 3 of them. And as we increase the temperature, the color of solution got darker and darker, suggesting there are more keratin extracted. So we estimated recovery yield, and the highest recovery yield we got was 70%, which is higher than most of the chemical processes published in the literature. So now we know we can extract the keratin from animal hair. We wanted to examine the characteristics that are relevant to cosmeceutical. One of the most important characteristics is molecular weight distribution. You really want to have a wide range of molecular weight distribution because you need a small, low molecular weight fraction for penetration of cortex restoration. And you need medium range molecular weight fraction for cuticle restoration. And you finish up by using high molecular weight fraction for coating. And then we wanted to compare against one of the best keratin-based hair care product out there. And FK Restore is one of them, manufactured by Plus Technology. They are kind enough to send us a sample. And this is a very high-end hair care product, mostly used at upscale hair salon. So it's pricey. In fact, the price is $1,785 a kilo. Where I'm coming from this chemical industry, we used to talk about selling polypropylene at few dollars a kilo. So this is a whole different ballgame. Picture to the right is our sample that we prepared. We don't have a price yet, but comparing against established products such as FK Restore, I thought we could get some idea. So first thing, we looked at the molecular weight distribution by using SDS-PAGE. FK Restore has a distribution from 17,000 up to 100,000, but it's shifted toward a higher end. The band to your right, COWT 1 is our sample. You can see a very thick, dark band all the way from top to the bottom, showing wide range of molecular weight distribution. So it looks like we passed first exam. We also looked at the very low end, which is lower than 1,000 Dalton, by using multi-top mass spectroscopy. This is the result for FK Restore. You can only see a couple of peaks. Here's the result for our sample. You see a bunch of peaks. Some of them are free amino acid, others are RUR peptides. So our sample has more low molecular weight fraction than FK Restore. The next we examine important amino acids are cysteine and cystine. And the difference is that cysteine is way up here, having disulfide bond, and that binds two alpha helices together, forming coil-to-coil structure. So this provides disulfide bond, which is the key to maintain the fibril structure. Now, the cysteine has another amino acid having thiol group. So this thiol group can have disulfide bond with the other keratin helix for restoration to form coil-coil structure. So both cysteine and cysteine play an important role in restoring damaged hair. So we looked at amino acid compositions for 3 samples. The green is the original keratin in hog hair. The red is our sample. The yellow is FK restore. You look all the way to the right. This is cysteine. So FK restore has quite a bit of cysteine residue, which is good. But what I want to stress here is that cysteine residue. Our sample maintains about half of what the original keratin used to have. But notice there's no yellow bar here. That is, FK restore has no cysteine residue at all because cysteine is destroyed by the chemical that they use in their process. So these are mainly, this is the main difference between our sample and FK restore. Now, based on these compositions, one can come up with a keratin model. Excuse me. So picture to your left, this is S-sulfonated keratin by FK restore. The cysteine is protected by sulfonic acid. Picture to your right, this is our sample. And since disulfide bonds are maintained, it forms coil-to-coil structure already. Whereas FK restore or keratin has to look for the pair to form disulfide bond. And here's a restoration mechanism by S-sulfonated keratin proposed by Keraplast technology. So this, let's say this is your hair, existing hair, then you buy FK restore and add to it, and you can form disulfide bond to restore your hair. But the key here is that the location of these disulfide bond has to be right positions. And they are not always guaranteed. When you mix them, you may have a wrong positions, in which case you end up having deformed keratin protein. Whereas in our case, our disulfide bonds are native, therefore they are in the right position. So that's another important difference. Now I'm going to end my presentation by saying a few words on green chemistry matrices using 2 matrices. One is the E factor, which shows how wasteful the process is. The second one is reaction mass efficiency, shows something about how efficient the process is. In the table, chemical process is based on the FK restore I was talking about. I took the numbers from their pattern application and scaled up to 1 metric ton a day of processing COWT feed. So as you can see from the table, for E factor and reaction mass efficiencies, our process, COWT process, is much less wasteful and more efficient. And I also added estimated annual energy consumption and CO2 emission. And we have 3 orders of magnitude less energy consumption against 3 orders of magnitude less CO2 emission. So in conclusion, our process is much less wasteful, more efficient, leaving less environmental footprint. Thank you for your attention.